Welcome, everyone. I know that we may have current Baxter families and prospective Baxter families who may view this Zoom. We are live and we're recording right now, and I'm so pleased to be here with JJ Rodriguez, Baxter's 3D geometry teacher and Textile Flex Friday cluster coach. JJ is the cornerstone of our math department. As chair of the department and also instructional leader, his classes really ask students to pursue excellence. They're inclusive. He always has these tricks and games that he plays with the kids, even just to open class, that are inclusive and engaging. He uses hand manipulatives. He doesn't just use hand manipulatives. He makes the students make hand manipulatives and really holds students accountable using also analog tools like journals and notebooks. He orchestrates open-mindedness by building in social structures that get kids to sit with new kids. This math major from Drexel University also holds a master's degree from National University in Teaching and Learning. He never stops learning himself and engages in PD ranging from personal finance to data-driven instruction. He adds much to the life of Baxter as the first faculty moderator of Dungeons and Dragons and Magic the Gathering after school as their coach. He's comfortable around fiber arts as he is around coding. And recently, when I walked into his classroom, he was learning and teaching students Kipu, the ancient Incan fiber-based computing system. He is the honors teacher for math, and with these ambitious students, they're exploring the intersection of the origins of math ideas and cultural influence. In 3D geometry, I've seen you have kids build sculptures to visualize shape. Get us started, JJ.
Yeah, so we just finished our first project in 3D geometry, so I thought I would bring in a couple of those. And I don't want to tell you what the project is. Instead, I want to present to you the projects that I got submitted. And my question for you all is, what do these objects have in common? So here's a square pyramid, square base, comes to a point. There's a cylinder.
Okay.
Rectangular prism or a cuboid.
Okay.
And a cone. And so I'll leave you guys to think about that for a second. What do these shapes have in common?
All right, so we're at this. What do these shapes have in common? Anna, are you prepared to be a student with Kimberly and I?
Always.
Awesome.
Lifetime learning.
Okay.
Jasmine's joining too.
Nice, nice. So what do these four shapes have in common?
Since I just opened it up, I don't know which four shapes I'm looking at.
Right here. These four shapes.
Well, let me see. I can't say that their lengths of the sides are the same.
Nope.
Nope. Let me see. How many are there in each item?
So each item theoretically is the item itself and then some calculations that go along with it.
Wait, did kids 3D print these?
Yeah, so some of them are 3D printed, some of them are handmade out of folders or poster.
Oh, they're all 3D.
Yeah.
They are all 3D. That's true.
Okay, there's one thing.
That's awesome. That's great.
Kimberly, you stole what I was going to say.
That's all right.
I think they're 3D.
What is...
I know.
Oh.
There's like volume.
Yeah, okay, talk to me about the volume.
There's space inside the shapes.
Yes, you got it. Can you put it all together?
That means...
Do they have the same amount of space?
They all have the same volume. Yes.
They do have the same volume. That's awesome. How did you do that?
So yeah, we've been working on deriving different formulas for different three-dimensional solids. Yeah. And so I had them choose, yes. We had them kind of choose different shapes, and then basically you can choose one part of the measurement, but then you would have to derive the other part. And I had them say, you have to equal exactly 1 liter. And 1 liter, I don't know if you all know this, I didn't know this before, is 1,000 cubic centimeters.
I did not know
1,000
that.
cubic centimeters. So,
I knew that.
oh, there you go. So then, the simplest way is a cube, 10 by 10 by 10. That would be 1,000. I said, you're not allowed to do a cube. You can do anything else.
Okay.
And so this is what we got. These all have a volume of exactly 1 liter.
Wow.
Good job.
So we could buy water bottles that are a liter in all 3 different shapes, all 4 different shapes.
And what's also really cool is I had them then calculate the surface area. And even though they all have the same volume, they have drastically different surface areas.
Like, give me an example. What's the smallest surface area?
Oh boy. Well, the smallest possible surface area is a sphere.
A sphere.
The sphere has the smallest possible surface area. And then the largest possible surface area would be something that really extends out in one direction. So probably this one has the biggest surface area out of all of these.
Yeah.
And I've had students who've made very, very wide objects before that are not very tall that would have an extremely big surface area.
So this would also, would you say this is less dense, or am I going in the wrong way?
Well, we're not yet talking about like weight, which is like where density comes in. But yeah. So when it comes to efficiency, the reason that things come together and like water droplets, for example, tend to be spherical is because that minimizes surface area for the same for the same volume.
Nice.
So a couple other things. Right here on the screen, I have some platonic solids. So the platonic solids are the only shapes you can make that use the same regular polygon over and over again. So the basic one is a cube, which is 6 squares. The tetrahedron, tetra means 4, it's 4 triangles. Octahedron, that's 8 triangles. Dodecahedron, which is 12 pentagons. And lastly, the icosahedron, if you like Dungeons and Dragons, that's a D20, 20-sided triangle figure. And any guesses on which of these could possibly stack to fill in space with no gaps?
To fill in space of just space?
So if you repeated the object, which of these could fill in space without leaving any gaps?
Well, the cube.
The cube, absolutely. Yep, 100%.
Is there more than the cube?
Is there more than the cube? That's really the question.
I see.
Yeah.
I see.
I wish that, you can, I wish that the tetrahedron could, but it seems like we run into problems with that fairly quickly.
You do run into problems with that. So the tetrahedron, if you look at it kind of exactly how it is on the screen right now, you're presented with this thing called the dihedral angle. And the dihedral angle is not what you would want it to be, which is about 60 degrees. It's not 60 degrees. So it turns out that the tetrahedron on its own does not fill the plane. But guess what? The tetrahedron with something else does completely fill in space. Can anyone guess what you would need to match it up with?
A carbon and a hydrogen.
Maybe. I
don't know. Doesn't it work with the octahedron?
That is exactly correct. It works with the octahedron. And here is kind of a visual for that. And it turns out that those two shapes perfectly fit together and create this larger shape that can then fill space. So this is the kind of thing that we like to talk about in 3D geometry, kind of think about how do things take up space, and then how do different constraints change that entire thing. So this is one of those where we wanted to kind of, this has some of the most constraints, and in fact, these are the only regular, so platonic solids that will fill in space. So it's kind of interesting that it's so limiting.
It is. So JJ, question, when was that figured out?
I believe the cubic honeycomb hasn't been known for a very long time. The octahedron and tetrahedron, I don't actually know when that came about. A lot of the study of regular shapes came around the bubonic plague era, so about 700 years ago. That is actually when they discovered, quote unquote, that the dodecahedron works. So this 12 pentagons situation. And it turns out dodecahedrons and icosahedrons also show up in things like virus structures. So viruses will often have this kind of shape around it. And even tetrahedrons, that dihedral angle is the same dihedral angle that you see in, oh boy, I don't know chemistry that well, but something that has one central node and then 3 corners.
Carbon atom.
Is it the carbon?
It is a tetrahedron. That's why I said carbon and hydrogen.
There you go. Okay, that does it. See, See, we work together. It works. So yeah, it's really cool how these things show up in real life, even though it seems like, oh, it's so constrained. So
That's super, super cool.
absolutely. I have a couple other things that we talked about in class. So yeah, I'll plop this away. One of the things that I like to talk about is how things shape, might change how things look and how things could exist in real life. So one of the projects that students chose that they got really interested in was, could Godzilla exist? And so throughout the course of this project, students figured out all sorts of different things. They basically tried to figure out an analog. So for some students, they said it was closest to the T-Rex because it was a large bipedal lizard, or a marine iguana because like there are no T-Rexes. So then that would already maybe imply that it wouldn't exist. Or a blue whale because it's so big, right? So based on all these different things, they then did some calculations. They said, okay, if Godzilla is so extremely huge, any of his length, we divide that by 200 to get that marine iguana that you see on the screen. And the interesting thing about dividing by length, length is one-dimensional, which means that any area calculation is two-dimensional. So you would have to, if you're scaling upward, instead of multiplying just by 200, you would have to multiply by 200 squared, or 40,000. So something extremely big. And that's just for two-dimensional things like blood pressure or steps on the ground. So from two-dimensional analysis, they said that the blood pressure of Godzilla would explode most industrial pipes, and that footsteps would completely just shatter Tokyo. Like, you would go through the ground. It wouldn't even couldn't even exist.
What are the students like when these discoveries happen in your class?
They are confused, but also I think that there's like an amount of joy to it, right? Like they get to see like, oh, like if I want this to be true, or if this could be true, like, oh, there are so many things that I didn't consider had to also be true. It's really interesting.
How do you start with your curriculum writing, JJ, for this level of engagement? Like, where's your beginning?
Yeah, so this analysis is all about like, how do you transform things in 3D? So back in 2D, we talk about things like rotations and reflections and dilations. And so turns out all of those things have analogs in 3 dimensions as well. And so what we then had to analyze is, how does that change the object itself? And so for the object, sorry, just admitting someone here. There you go. So reflections usually don't change very much. Rotation usually doesn't change very much. Where does the interest come in? Dilation, making things bigger, making things smaller. And understanding things like the square cube law is really where I wanted to get. And so we got to the square cube law by analyzing this and saying, okay, well, if the length is multiplying by 200, the area is multiplying by 40,000, so the volume or the mass would have to multiply by 800,000. So, you know, these huge numbers, right? And so how does that change all of these different calculations? Well, that's kind of what we talked about in class.
Oh, very cool. Very cool.
I'll show, I have one or two more. So trigonometry is similar. Trigonometry, turns out we're really good. We kind of nailed it with 2 dimensions. So in 3D, the way that we kind of talk about trigonometry is, okay, how do we use trig to make our world easier to understand? So these are some student projects where they picked, I believe, 20 or 40 points to kind of what are they called? Latitude and longitude. So you see Maine on the left here, and then the United States on the right. And they used different map projections to say, okay, well, we have this spherical globe, this roughly spherical globe. How do we unwrap it to make something that we can understand? So on here we have the Cassini projection, which is really good for things that are focused on north to south. So this is Maine in the north to south projection. And then I had a student who was really, really interested in navigation last year. She was going to school to become a pilot. And so she got really into this Lambert conical, which is actually how you do real life navigational maps for small areas and so even Maine, quote unquote, and it is shaped differently. It's because it is focused not on distance but on direction. So because it's focused on direction, it makes it easier for navigational maps.
Interesting.
And then kind of on the opposite side, the USA over there on the right looks super different. Doesn't
Yeah.
look like what it's supposed to look
Right.
like. But this projection allows you to draw a line between any two points in the US,
Yeah.
and that represents the true spherical distance
Interesting.
over the top of the
Wow.
sphere between those 2 points.
Yeah.
And
Yeah.
you might be saying, I don't see the trig. Well,
Mhm.
behind it, you get all these scary
Mhm.
equations. Now, I will say
Mhm.
at this point in our curriculum, the students weren't deriving these equations,
Okay.
right? These are already known and named projections.
Mhm.
But we were working with Desmos, just a regular old
Yeah.
graphing calculator,
Yeah.
and trying to test the limits of the function capabilities on
Mhm.
Desmos.
Mhm.
And so these are just different snippets of code from our
Mhm.
Desmos
Yeah.
workbooks.
So this looks really complex, JJ.
Yeah,
Math is a language.
absolutely.
And I feel like when I was a kid in math, there were right answers. How do you inspire engagement when the kids get it wrong?
Oh, I love when kids get it wrong
You
because
love when
I
kids get it
do.
wrong.
I do, because then I get to figure out what happened, right? It's a little puzzle for
Yeah.
me. So I can
Mhm.
say, almost always, I can look at a student who gives me a wrong answer and say, I
Mhm.
know exactly what you did. You divided by 4
Yeah.
instead of
Yeah.
multiplying by 4. And it's, I try to level with the student and say,
Mhm.
you're one step away. Oh, I know exactly where you are.
Yeah.
And so, yes, there are right and wrong answers, but
Mhm.
oftentimes they are almost correct answers,
Mhm.
or the
Mhm.
steps were, 90% of the steps were correct.
Right.
And there was something in the middle or in the beginning. If it's in
Right.
the beginning, it's a little harder,
Right.
or at the end that they just needed to fix.
Yeah. Yeah.
And so
Yeah.
I always try to make sure I can level with the student, figure out exactly what happened, and
Yeah.
go from there.
Yeah. Yeah. That's so, so cool. What's
So I have
hard
a question. Can I ask a question?
Oh,
Sure.
So with the kids coming into your classroom, JJ, some of this seems like it would be very new to the students. Is
Yeah.
there a broad diversity in terms of student experience when they come into your classroom with stuff like this?
Absolutely. The majority of students for this project did the Mercator projection,
Mhm.
for example, which is simply the latitude is your y value and the longitude is your x value.
Mhm.
And that was a totally accurate map projection that is still used today. We see
Mhm.
Mercator maps all over, all over. And so I have them, instead of going through the intense trig that you see on the screen here, I have them talk about what are the distortions that the Mercator map does. Like, how is the Mercator map, quote unquote, wrong? Because every map is wrong,
Mhm.
simply by
Mhm.
making it
Mhm.
two-dimensional.
Right.
And so I have those students usually focus more on, like, why is this not ideal?
Yeah.
And go along those lines. And then for the
Yeah.
students who really want the challenge, they go and find all of these functions that need to work together.
Mhm.
That's a great question.
Yeah, that's
That's
awesome.
cool.
Do you
Yeah,
have
well
any more to
done.
show us?
I think I might have one or two more.
Sure.
So near the end of my course, I try to talk a little bit about topology. So this is where we kind of break the rules
Mhm.
of objects. And so, for example, there's this common joke that to a topologist, a coffee cup and a donut are the same.
A coffee cup and a donut are the same.
Yeah.
Okay, I'm trying to stick with you here.
Yeah. And so it turns out, and this is a comic that was drawn by a student who did it instead of a donut, they did it with a traffic cone. That the rules of topology say that you're allowed to squish objects. You're allowed to
Okay.
kind of give them a twist. You can give them
Okay.
stretches. What you can't do is you can't rip open holes or make new holes.
Okay.
So breaking those, so as long as you don't break any of those rules, you can say that two objects are topologically equivalent.
Okay. So
Yeah.
there's one opening
Yes.
and there's a surface.
And that's exactly what a donut is, and that's exactly what a coffee cup is.
A ring.
A ring.
A
Yeah.
ring. So, okay, interesting.
So this is no different. So a traffic cone to a topologist is no different than a circle with a hole going through it. Exactly, or a ring.
It's just with the coffee cup, it's distorted on one side of the ring.
Yeah, exactly.
And because it doesn't poke all the way through, it's just still only one hole.
Yeah.
Okay.
Yeah. So topology is really fun for that reason. I had another student a couple years ago. They created this topological model of a shape that actually can't exist in 3D. So this is just a really good, this is a really
It
close.
cannot.
It cannot. Yeah, no, this shape is not actually the true thing. So this is a Klein bottle, except it's not.
Klein bottle. Okay.
A Klein bottle is kind of like a Mobius strip. Have you ever taken a strip of paper and twist it and seen that it all so
Car like that.
yes, they do. Absolutely.
Yeah.
So this similarly is entirely one-sided.
Yeah.
So like the inside is the outside of this
Yeah.
object.
Yeah.
The one qualifier with that is that right here, this has to simultaneously be a hole and not be a hole.
Okay. Okay.
And so because of that, that's why it can't exist in a three-dimensional sense, but we can still make a pretty good model of it.
Sure.
It's pretty neat.
Yeah. I have a couple more
Please tell
questions.
me your questions.
But do you have more here?
I think I had one last
What
one.
is yours?
So my last project was graph theory and train stations. So graph theory, I kind of am really breaking the rules of 3D here now, and I'm saying, what if we took away all the dimensions? And we said, okay, purely you have these objects that are dots connected by lines or vertices connected by edges. And how do we communicate information with that? And so we go through all of these different steps about edge coloring, vertex coloring, sets, supersets, all kinds of things that you can do with vertex edge graphs, paths, circuits, etc.
And they don't have to be looped.
They don't have to, well, sometimes they can, sometimes they can't. So this project was specifically, okay, here is $1 billion to make a train system for Maine. How can you meet these 12 criteria?
Great.
Yeah, it was a really cool project and students got really into it. It's kind of maybe a little hard to tell on here, but every vertex that's next to each other is a different color.
Yeah.
And similarly, the edges that connect them, if any two, so it's tricky. Edge coloring is that if you have two vertices that are both connected to the same vertex, they can't have the same color on those edges. So this has different edges to represent radio frequencies. It has different colors to represent train times. And then there's this thing called domination sets that says, okay, well, you don't need a security station at every station. And like, yeah, you could put one at every other station, but could you get even more efficient with that? So these are different kind of problems that we were analyzing, and the students really enjoyed this train station project.
That's so cool. I love that. I want that for our state.
Yeah. Oh, yeah, absolutely.
You're like putting seeds of ideas
100%.
that make math relevant to improving our community.
That was the hope. Absolutely.
That's so awesome. Well, I feel like I have an answer from you about it's hard to inspire students to be curious about math, but you are finding a way to do it joyfully and with hope. What makes you so passionate about working with teenagers? Because when I walk into the classroom, I see it on your sleeve, JJ.
Yeah.
What are you working for?
Teenagers are just really close to being adults.
Yes.
And so I want to make sure that before they walk out of campus, that they don't walk out and say, well, I'm never doing math again. I want them to be able to see where math is in the real world. And like maybe the next time these students look at a subway map, they'll remember this project. Right. And they'll be like, okay, oh, haha, did you know that you could do this with the vertices and you could do this with the edges? Like it's a fun thing. So I wanted to kind of send students out of here with like a love and a curiosity for math.
And I'm also hearing you say that you're taking a little bit of the mystery away so that it becomes accessible.
Yeah.
So they're awake. You're giving them a language to be more awake in terms of how the world is operating or how the world can be built.
That is the hope, yeah.
Because you're giving them a way to build pieces of the world through these assignments that are, I would say, a little unconventional. Would you say?
Oh, 100%. No.
Yeah. Well, I want to give folks a chance to ask questions. Jasmine, Anna, and Kimberly, if you have any questions for JJ, I'm going to stop the share right now.
There we go.
And Christian. Hi, Christian. Any questions for JJ?
I actually have another question. And that is, thinking in terms of these magnificent shapes playing out in organic form and presumably in other classes in the building. Can you talk a little bit about how you might be kind of collaborating with your fellow teachers in the way that you think about math and they're thinking about, engineering classes or science?
Absolutely. Yeah. So I have gone to both Wiley and Sunny to learn how to make things like this myself in SolidWorks, and like learning how to make shapes in SolidWorks, how to kind of do a proof of concept. And SolidWorks also can find a volume for you, which is kind of cool,
Oh.
if you know the buttons to press. So it was really helpful for kind of coming up with some of these myself before showing them to the students. And similarly, like I have worked with Wiley before to use Desmos, the same thing that we made maps with, to figure out like how do linkages work, how do pistons and pulleys work, and like what are the trig functions behind it. So there's definitely a lot of movement between design and math and how we can support one another with those. And I'm always open to finding even more ways to do that.
The thing I want to highlight is sometimes when we think about math, we think, okay, you're going to learn this equation and then you're going to work through this equation and everybody's got the same worksheet and the same boxed answer with work shown. But what I'm seeing here is you've got a core concept. All of those are 1 liter.
Yes.
And now the student's assessment or project, all the kids in the class are interpreting that in a slightly different way.
Yes. Like this student and this student had to go through very different processes.
Right.
Yes.
Right. And so now in terms of having a community of learners, they're not just sort of like mass reproducing each other, but there's actually a reason for the kid who produced this one to talk to the kid who produced this one. So not only are they learning the core thing, but because of their individual sort of extrapolation, they have a reason to learn from each other.
Yeah.
So,
Absolutely.
and it's the same thing with your subway development as well.
Yeah.
So like, why did you choose a subway system that was like this? And why did you choose a subway system that's like that? And I think that that is just an amazing thing that you don't have cookie cutter things happening.
I appreciate that.
So
That's the hope. That's what I'm trying to do.
Really awesome. Well, I think that this really shows off drawing out students' own motivations, students' own lived experiences into like intersecting with some of the, I want to say abstract concepts, right?
Yeah.
But now you make them grounded in a little more reality. So thank you so much, JJ.
Of course, of course.
This has been awesome. And
Thank
to
you.
everybody who's in the audience, I'm hoping to send you out a little feedback form, and I hope you'll take the time to share your feedback with us. Thanks for spending your lunchtime with us.
Thank you all so much.